So this is part 2 of the overview for 7.1. I'm having storage issues on my computer and it's cutting me out because I'm using a document camera. I think we have it fixed now. Here we go on take 3 to get 7.1 done. So the other video ends off right here where I was mentioning if we add these two together, then we get the 22.7. And if we take the 22 and 3/10 and subtract 4/10, we end up with this 21.9. What that is saying is helping us to get oriented to that mu is going to be between a range, a lower number and a higher number. They mention a little bit more. They say also it could be a proportion, and a proportion can be written as a decimal, lower and upper. It can be written as a percent, lower and upper. And it can be written as a middle number, plus or minus how much ever is indicated in the problem. Either the interval contains the parameter or it does not. It's still a little bit frustrating, but we're still guessing. We think our answer, the true mean, is going to be in there. Again, we're just doing statistics and trying to make the most of our answers. A degree of confidence, which is usually a percent, must be assigned before an interval estimate is made. For instance, you may wish to be 95% confident that the interval contains the true population mean. But then another question arises. Why 95? Why not 99? Or why not 99.5? If you desire to be more confident, since like 99 or 99.5, then you must make the interval larger, like a bigger net, to be able to catch wherever that mean actually is. For example, a 99% confidence interval for the mean age of a college student may be this. So hence a trade-off occurs. This is lower than where we were up here. This is higher than where we were here. To be more confident that the interval contains the true population mean, you got to make it wider. So here's some more words. Again, a reminder that you can start and stop. Write this down on index cards, sticky notes, highlighter, whatever you'd like to do. I've got a little bit of both going on over here. A confidence level of an interval estimate is the probability that the interval estimate is going to actually contain what I'm looking for, assuming that a larger number of samples are selected and that the estimation process on the same parameters repeated. Mainly a level, like a 95% level. The interval is the specific interval estimate, a lower number and a higher number, of a parameter determined by using data obtained from a sample and by using the specific confidence level you have chosen here of the estimate. I'm doing a lot of reading. You can shut this off and just read it to yourself. But here we go on some more reading. Interval levels conducted in this way are called confidence intervals. 3 of the common ones are 90, 95, and 99. I'm going to get you to write some information on your formula card very soon. A population has a fixed value for the mean or proportion, and when a confidence interval is constructed, it's either going to include it or it won't. We're still guessing, but we're guessing at 95%. If it were possible to construct a 95% confidence interval for a statistic such as a mean or a proportion for all the samples of a specific size, we can conclude that 95% of them would contain what we are looking for. You can be 95% confident that the population mean is contained within that interval when the values of the variable are normally distributed. So we're getting to, so what does this mean for me? So what it means for us, I'm just going to leave these here. What it means for us, you can't see those. I want you to see those in just a second. This is definitely a page you may want to start and stop the video. You've got to soak this in. It's got to make clear sense to you, and then you need to write it down in your words and what you discovered and what makes most sense for you. So it says the value used for the 95% confidence interval is 1.96. Well, I'm probably feeling pretty confident myself about how to use this chart. And so when I see 0.95, I get all sorts of confident. And 0.95, I come right here and I'm like, oh yeah, it's exactly between them. I remember reading, go with the larger. And when I go with the larger, it's 1.65. And that is not what it says here. Oh. So something's up, something is different, and we're now talking about confidence intervals. We have been dealing with z-scores and messing around with them, and I told you down here it is what it is. If we're working on a two-tailed or another number where we're looking for greater than the z-score, we do something else. Here is yet another something else. We are in Chapter 7, and so in Chapter 7, it's always good to come over here and look and see what all is going on. This thing may scare us to death right now, so let's just ignore that. We'll come back to that later because it's no big deal. So then I think maybe I read it wrong. So 99% confidence interval and the value is 2.58. So I go over here and I'm so excited because I know how to read this thing now, and I'm at 0.99, 0.99, 0.9. Oh, here it is. That one's 2 away, that's 1 away, it's this one. And so if it's this one, I'm at 2.3, and when I go all the way up, it's 2.33, and that is not what it says. So what is going on? What are they talking about? And how are we going to find this thing? Well, part of this scary-looking formula for right now, part of this scary-looking formula contains a z sub, and that's a little different, because normally we've just had z. Now we have a z sub, and it's got an alpha divided by 2. Well, it's the same thing over here, so once I know it for this one, I got it. And then the rest of this really isn't that scary, because I've had x bars before, I've had some sigmas and some n's. I can do this. But right now we need to talk about what the heck is z sub alpha over 2. So when I look back over here, it talks about it comes from Table E. It is based on standard normal distribution. Confidence interval, uh-oh, here we go. It's read z sub alpha over 2. It is used as, or in, the general formula for confidence intervals, what I was just showing you. And the Greek letter alpha represents the, total area of both tails of the standard normal distribution curve. And alpha over 2, or alpha divided by 2, represents the area that each one of the tails. Okay, so we've got this new thing. You're writing it down, you're highlighting it, and this value z sub alpha over 2 is called a huge, right here, critical value. The relationship between alpha and the confidence level that is stated is going to be some percentage, decimal value, a minus is going to go on, and 95 is mentioned, and then all of this, and something's going on, and then somewhere in here, it's talking about calculated on the other side, and it's margin of error. Okay, so hang on to that. Let's stay right here. So let me go to this one. We are going to go use our chart. And when we go use our chart, trying to cover up some stuff here. And we go use our chart, and we're looking at this drawing here. And I'm wanting to have my range be 95% confident that the mu, or whatever I'm looking for, is within it. I need to know 2 z values. We'll be talking about where do we get these numbers and what do we have going on here. But then they mentioned a 1 minus, and what the heck is going on? And so if 95% of our area is under this curve, then the rest is left for these guys over here. So if I say 1 or 100, either way, to subtract this off, can you agree that I end up with 5%? But it's not 5% here and 5% here, it's 5% split between the two. Remember that thing a while ago? Z sub alpha divided by 2. This is our alpha. But I don't want the alpha, I need half of it. And so that means over here, there's 2.5%. And over here, there is 2.5%. But good grief, they had a number up here, 1.96 with this 95, and it doesn't make sense to me. Let's make it make some sense. When I want a number, and when I'm looking for what is this number here, and what is this number here, there are a couple of ways to go about it. One thing we can do, because remember, when we're looking at our chart, everything that we see on this chart is it is what it is. It's from here back on the left-hand side. So I prefer finding the one over here, but it would work for either looking at what's going on right here or what's going on right here. I'm going to go ahead and play around with what's going on up here. And I have to have you agree with me that to get me all the way up to here, I had 95% plus half of the leftover, and that puts me at 97.5% to get me all the way up to here. So now, when I go look in my chart at 97.5% or 0.9750, I got my confidence back, and I'm going to go 0.9750. looky there, 9750. It is located at 1.96. And that's that number right there that didn't make sense a while ago. So 1.96 is what we're going to use for our 95%. We're also going to find, if we go to the negative side and go to negative 1.96, do y'all see what's at the negative 1.96? It's 2.5%. Look right there. That part over there represents 2.5%. You're going to start finding little tricks, and if we were face to face, you could ask me your questions. You can always still email those, even during the homework. You can do the Ask My Instructor. You can send me emails about this, take screenshots of what's confusing. But I want to do this little ditty again. So I've already got it started here. And this one's for a 99% confidence interval. And for it to be 99%, I would need to take my 100% minus my 99%, and I get 1%, and that's going to be my alpha. You really have to truly understand, what am I doing, where are my numbers coming from, and could you replicate this on your own? But in this particular situation, we don't want z sub alpha, we want z sub alpha divided by 2. So I need to take my alpha, which is a 1%, or however you want to see it. We're going to divide it by 2, or you can call it 0.01 divided by 2. Either way we go, this is going to turn into, as I've already written in, 0.5% and 0.5%. To find what is that z sub alpha divided by 2, we already know from looking up here that the 99% is not going to be this number, just straight looking it up. I've got to do a little manipulation. And so I like seeing it as my 99 plus this 0.5 to get me all the way up to this z value. And so 99 plus 0.5% gets me at 99.5%, otherwise known as 0.9950. So when I go back to my chart, I'm looking for 0.995, 0.99, 0.99, 0.995. Here's one. It's dead center. It's one away from that one, and it's one away from this one. So I go with the upper one, and it's at 2.5, 2.58. And that's exactly what they said it's going to turn out to be. So you've got to make yourself some kind of huge note that this thing that we've started talking about, this alpha divided by 2, we're going to end up writing it in this area on Chapter 7. But it's not time yet. When we get to that point, I'm going to tell you what to write and where you can consider writing it. Right now, the big thing is, do you understand what just happened? I would definitely hit pause and think on it for a moment. One more thing I need to show you in this section. There's a thing called a margin of error. It's called the maximum error of the estimate. It's the maximum likely difference between the point estimate of a parameter and the actual value. In the age of our students, where we had a confidence interval, or it was written this way, it is the 0.4, this add-on piece, add-on or subtract-on part, is the margin of error. In the proportion of the example where the confidence interval is this, or it was written this way, this back-end part, the plus or minus part, is going to be our margin of error. The formula for confidence intervals and margins of errors are shown in the next section. We've looked at these. At the top of the page, I'm going to go ahead and say just a little bit more. Confidence intervals can also be represented by using parentheses. For example, you could do the one for age as parentheses lowest range, highest range number. And then for these, the ones that we were talking about, the proportion, the lowest percentage, highest percentage. And my note is we need to go on to 7.2. Actually, I'm going to hit stop, and then you'll have more directions on what to do for 7.2, and that's the part down here.